Welcome to the Deep Dive. Today we're digging into a fascinating collection of AI research papers. Think of it as a curated book review, but focused entirely on AI.
Right, and not just the theory. We're looking at how AI is actually being applied, the real world nuts and bolts.
Exactly. So who is this for? Well, if you want a solid grasp of current AI research without wading through dozens of academic papers, you're definitely in the right place.
Yeah, or if you're a professional, maybe in transport, manufacturing, finance, logistics, even healthcare, you'll see how AI could, impact your field directly.
Absolutely. And researchers too, maybe looking for a consolidated view or just anyone curious about how this technology actually works in practice.
hmm The core theme weaving through all these papers is really about practical application, exploring what AI can do now, the challenges it faces, and where the advancements are happening.
It's about implementation, but also, importantly, acknowledging the limitations. What can it do yet?
Precisely. So let's dive into the chapters. Chapter 1 kicks off with automated machine learning, or AutoML.
AI building AI, essentially.
Sort of, yeah. The goal is to cut down the manual effort for data scientists, automating the process of building effective machine learning pipelines.
How does it do that?
Well, it uses techniques like Bayesian optimization. Think of it as a smart search method to find the best model configurations efficiently.
But I gather it's not perfect,
Yeah,
especially with non-numeric stuff.
right. Bayesian optimization works best with numbers. For configuration spaces with, say, categorical choices, you might need other approaches, maybe random forests or neural networks to handle that mapping.
Okay. And there are other methods too.
Oh, yeah. Evolutionary algorithms are another big one. They use ideas inspired by natural selection, exploring lots of possibilities at once. Good for really complex search spaces.
And data prep is still key, I assume. Feature selection, engineering.
Absolutely fundamental. Garbage in, garbage out still applies. AutoML often includes steps for that too. Then there's meta-learning.
Learning from past experiences.
Exactly. Using results from similar datasets to suggest good starting points for a new problem. And you can even have human-in-the-loop AutoML where experts guide the process.
Interesting. But it has limits.
Definitely. Current AutoML doesn't always beat simpler, hand-tuned models, especially for tricky problems with multiple objectives. It's still an active research area.
Makes sense. Okay, chapter 2 moves to sequence-based learning. This is about time, right? Data that unfolds over time.
Exactly. Time series data. It's everywhere now, thanks to sensors. Think health monitoring, industrial processes, even education and entertainment.
And traditional statistics struggle with this kind of complex, multivariate time data.
They often do, yeah. That's where deep learning models shine. Things like recurrent neural networks, RNNs, and temporal convolutional networks, TCN.
You can learn the patterns over time.
Right, they're built to capture those temporal dependencies, even complex ones. The typical pipeline is clean the data, extract useful features, then use a model for classification, regression, or forecasting, and finally, interpret the prediction.
Any cool examples?
The papers mention things like detecting cognitive load in drivers from sensor data, classifying activities based on how someone uses a handheld tool, or even recognizing handwriting from a smart pencil.
Wow. And you mentioned RNNs and PCNs. What's the difference there?
Well, TCNs can often be trained more in parallel, making them efficient, especially for fixed-length sequences. RNNs kind of compress the history as they go, step by step, which can be good too.
But RNNs have that vanishing gradient problem sometimes.
They can, yeah. Especially with long sequences, gradients can either disappear or explode during training, making learning difficult. But there are techniques like LSTMs and GRUs designed to help with that.
Okay. And what about when the test data is different from the training data, like a different environment?
That's where transfer learning and domain adaptation come in, trying to adapt the model to the new situation. Metric learning and, crucially, model interpretability are also big challenges here. We need to understand why the model predicts what it does.
Always important.
Okay.
Chapter 3, learning from experience. This sounds like reinforcement learning.
That's it, RL. The big difference from supervised learning is there's no labeled ground truth. The AI agent learns by trying things out and getting rewards or penalties.
The exploration versus exploitation dilemma.
The core challenge. Do you stick with what you know works, exploit, or try something new that might be better, explore? It's a constant balancing act.
How do they manage that?
Techniques like upper confidence bound, UCB, and Thompson sampling provide principled ways to balance. There are also memory-based approaches like never give up or go explore for more complex situations where the rewards might change.
And model-based RL,
Right, that's where the agent tries to learn a model of how the environment works. It can then use that model to plan ahead, which can be more efficient.
Like playing chess in your head.
Kind of, yeah. Monte Carlo tree search, MCTS, is often used here, especially in games like Go. It explores possible futures.
And hierarchical RL, breaking down big tasks.
Exactly. HRL uses the idea of option sequences of actions to achieve subgoals. Makes learning really complex behaviors feasible. Think teaching a robot to make coffee, you break it down into steps.
What are the big hurdles for using RL in the real world?
Safety is a huge one. You can't just let an RL agent explore randomly in a self-driving car, for example. Policy generalizability, making sure it works in new situations, is tough too. And just defining the right reward signal can be surprisingly difficult.
And learning from just old data. Offline RL.
Yeah, that's another big challenge. How do you learn effectively if you can't keep interacting with the environment? Lots of work going into that.
Okay, Chapter 4 tackles a common headache. Learning with limited labeled data.
A very common headache. Getting lots of perfectly labeled data is expensive and time-consuming.
So what are the strategies?
Two main ones discussed are semi-supervised learning, SSL, and active learning, AL.
How do they differ?
SSL uses the unlabeled data directly in the training process, trying to learn the underlying structure. AL, on the other hand, intelligently selects which unlabeled samples would be most beneficial to get labels for. It asks the human expert for specific labels.
Okay, tell me more about SSL first.
Classical methods include things like generative models, methods that try to put the decision boundary in low-density regions between clusters, graph-based methods. More recently, deep SSL uses techniques like self-training and consistency regularization.
Consistency. Like making sure slight variations get the same prediction.
Pretty much. Using data augmentation, like slightly rotating an image, and enforcing that the model's output stays consistent. Mix match and fix match are examples.
And active learning. How does it pick the samples?
Usually based on uncertainty. It picks the samples the model is least sure about. Or sometimes it picks samples that best represent the overall data distribution. The goal is to get the most information bang for your buck, reducing annotation cost.
How do you measure uncertainty in deep networks?
Bayesian neural networks, or techniques like Monte Carlo dropout, can give you uncertainty estimates.
Could you combine AL and SSL?
Absolutely. That's a promising direction, using AL to select samples and SSL to leverage all the remaining unlabeled data. Best of both worlds, potentially.
Makes sense. Chapter 5 shifts gears to uncertainty quantification, or UQ. Why is this so important?
Trust. If an AI system is making critical decisions, like in medicine or finance, we need to know how confident it is in its predictions. It's also becoming key for regulatory compliance, like the EU AI Act.
Where does the uncertainty come from?
All over the place, really. The data itself might be noisy, the model might be misspecified, the training process has randomness, even the task definition can be ambiguous. There's data uncertainty, model uncertainty, specification uncertainty.
How do you measure it?
There are different approaches. Some modify the data, some modify the model architecture, some analyze the model after training, post hoc. Bayesian inference is a core statistical framework.
Using prior beliefs and updating them with data.
Exactly. You end up with a posterior distribution that represents uncertainty. In deep learning, true Bayesian inference is tough. So people use approximations like Bayesian neural networks or Monte Carlo dropout, like we mentioned, for active learning.
And how do you know if your uncertainty estimate is any good?
There are metrics for that, like negative log likelihood, NLL, and expected calibration error, ECE. ECE checks if a model that says it's 80% confident is actually correct 80% of the time.
But UQ isn't the whole story for trustworthy AI.
Definitely not. It's a crucial piece, but you also need robustness, how it handles unexpected inputs. Fairness, privacy, explainability. It's a multifaceted problem.
Right. Okay, Chapter 6, Process-Aware Learning. This involves process mining.
Yes. Process mining analyzes event logs, records of what happened when to understand and improve real-world processes. Think tracking orders in a supply chain or patient pathways in a hospital.
What do you do with it?
Three main things. Discover the actual process flows, check if the process conforms to a predefined model, and enhance the process by finding bottlenecks or deviations.
Sounds powerful, but challenging with huge logs.
Oh yeah, big data is definitely a factor.
Yeah.
And you want the discovered models to be good. They need to fit the data, fitness, not allow behavior that didn't happen, precision, generalize to new cases, and be understandable. Simplicity?
And it can look at cause and effect, causal inference.
That's an emerging area, moving beyond correlation to understand why things happen in the process. AI can also be used for prediction, like predicting the next step or the outcome of a process. Context-aware learning using Bayesian networks is one approach.
So it's combining data mining with process knowledge.
Exactly. That's the idea behind process AI.
Next up, Chapter 7, Combinatorial Optimization, finding the best needle in a haystack of possibilities.
A very good analogy. It's about finding the optimal solution from a discrete set of choices. Things like vehicle routing, scheduling, network design. Many real-world problems fall into this category.
Now, these are often really hard problems, NP hard.
Many are, yes, meaning finding the absolute best solution can take an astronomical amount of time as the problem size grows.
So how do you tackle them?
Several ways. Heuristics are often used, smart rules of thumb that find good solutions quickly, but without a guarantee of optimality. Then there are exact methods, like branch and bound, which systematically search for the provably optimal solution, but can be slow.
Branch and bound.
It involves breaking the problem down, branching, and calculating bounds on the best possible solution in each subproblem to prune away parts of the search space, bounding. And approximation algorithms offer guarantees. They might not find the absolute best, but they guarantee a solution within a certain factor of the optimum.
The chapter also mentions flow models and decision trees.
Right. Flow models are great for representing movement goods, data, whatever, through networks, finding maximum flow, for instance. Binary decision trees can sometimes represent the feasible options in an optimization problem.
And the pooling problem.
Ah, that's a classic complex example involving blending ingredients from different sources to meet quality specs while minimizing cost. Lots of tricky constraints.
Okay, data is crucial. Chapter 8 covers data acquisition and preparation. Back to basics, almost.
But incredibly important basics. AI is nothing without good data. The chapter looks at different ways to get it.
Like manual annotation. Experts labeling data.
Yep, the classic way. High quality, potentially, but costly, slow, and needs domain expertise.
What about generating data, simulation?
Physical simulation is another route. You create a virtual world or model, like simulating soccer players or how X-rays interact with materials to generate synthetic data. Needs significant upfront programming effort, but then you can generate lots of data.
And data augmentation, just tweaking existing data.
Right. Simple transformations like rotating, scaling, changing brightness. It increases data quantity, but doesn't really add new knowledge. Still very useful, though.
We already touched on active learning for smarter labeling. What about knowledge modeling?
That's about linking data with semantic meaning, often using structures like semantic networks, defining what a car is, its parts, its features, at different levels of abstraction. It helps structure the data and embed domain knowledge.
So different methods have trade-offs in quality and effort.
Exactly. Choosing the right approach depends on the specific problem, resources, and required data quality.
Chapter 9 brings us back to safety. Assured resilience in autonomous systems, especially cars.
Yes, a major focus is autonomous driving. Perception, understanding the world through sensors, is a huge challenge due to weather, lighting, unexpected objects.
How can AI be made more reliable here?
One technique discussed is ensemble distribution distillation. Instead of running multiple models in ensemble to get uncertainty estimates, which is slow, you train a single model to mimic the uncertainty prediction of an ensemble, much faster for real-time use.
Did it work?
The research shows promising results using object detection models like YOLOV3 in simulators like CarLA. They looked at scenarios like red light violations and random objects appearing.
How do they evaluate if the uncertainty prediction is good?
By correlating the model's confidence scores with actual performance metrics like precision and intersection over union, IOU, higher confidence should mean better accuracy.
And dealing with things the car has never seen before. Out of distribution detection.
Crucial for safety. ODE detection aims to identify inputs that are significantly different from the training data, signaling that the model might not be reliable. They experimented with various datasets to test simple ODE strategies.
Makes sense. Okay, Chapter 10. Robust indoor positioning. Moving away from cars into buildings.
Right. Think factories, warehouses, hospitals. GPS doesn't work well indoors, so you need other methods.
What methods? Cameras, sensors.
Those exist, but can struggle if the environment changes or things get blocked. The chapter highlights radio-based methods, specifically using channel impulse responses, CIRs. Instead of just measuring signal strength or time of arrival, CIRs capture how the radio signal bounces off walls and objects. This multipath information contains rich spatial detail.
So it works better when the direct path is blocked, non-line of sight.
Exactly. Traditional methods like TDOA elaboration often fail in NLOS conditions, but CIRs can provide much higher accuracy by analyzing the signal's entire journey.
Interesting. Chapter 11. Comprehensible AI for Multimodal State Detection. Detecting human states, like emotions.
Yes, effective computing. Detecting complex psychological states like cognitive overload, stress, or emotions is hard.
Why so hard?
Humans express states differently, subjectivity. Collecting good data is challenging, and building accurate models is complex. The key is often integrating multiple modalities.
Multiple data sources.
Right. Subjective reports, how you feel, performance data, how well you're doing a task, physiological signals, heart rate, skin conductance, behavior, eye movement, facial expression. Combining these gives a fuller picture.
The chapter mentions a data set, 80 base.
Yes, a multimodal dataset specifically for cognitive overload detection. It includes ECG, EDA, respiration, video, eye tracking, and more, collected during tasks designed to induce overload.
And the results show combining modalities helps.
Generally, yes. Fusion techniques often outperform single modalities. They also looked at interpretability, which features from which modality are most important for prediction, and how models behave under distribution shift, like training on one task and testing on another.
So, potentially useful for wearables that monitor stress or focus.
That's a key application area, yes. Using wearables or sensors integrated into environments like car dashboards.
Okay, Chapter 12 heads into medicine. Robust and adaptive AI for digital pathology. Analyzing tissue samples.
Exactly. Using AI to analyze digitized microscope slides, whole slide images, or WSIs. Tasks like finding tumors or segmenting different tissue types.
What are the challenges there?
WSIs are enormous, gigapixels in size. Processing them is computationally intensive. Another big issue is robustness, ensuring a model trained on images from one scanner works well on images from a different scanner, which might look quite different.
How did they address the scanner variability?
They created a multi-scanner dataset specifically to test model robustness.
And for adapting to new tasks quickly, like a rare tumor type.
They explored prototypical few-shot classification. This approach can learn to classify new categories using only a handful of examples, which is great for pathology where labeled data for rare conditions might be scarce.
How did it compare to standard methods?
It showed promise, especially in adapting to new tasks. They also looked at using things like the Mahalanobis distance to gauge prediction reliability on potentially out-of-distribution data from different scanners.
And handling the massive image size.
Different strategies. Processing the image in small tiles, using overlapping tiles, or using superpixels to group similar pixels first, reducing the computational load.
Chapter 13 revisits autonomous systems, focusing on dependability and safety again.
Right, particularly dependable reinforcement learning for autonomous driving. They present a whole pipeline, generating challenging driving scenarios, learning safe policies, and verifying them.
A testing environment.
Yes, Driver Dojo. It's a configurable benchmark built on the Sumo traffic simulator, designed to create diverse and difficult situations for training and testing RL agents.
And safe RL algorithms.
They introduce Safety QN. It learns safety constraints alongside the main driving policy, aiming to explicitly avoid risky actions. A claimed benefit is better interpretability because risk and utility estimates are somewhat separated.
How's it tested?
In various scenarios generated by Driver Dojo turns, roundabouts, highway merges, things like that.
And formal verification, proving safety.
They also discuss Safe IPER, which combines deep RL with decision trees to get more interpretable policies. For certain linearized versions of the system dynamics, they can apply formal verification methods to provide stronger safety guarantees.
Moving to energy now, Chapter 14. AI for stability optimization in LVDC microgrids. Low-voltage DC grids.
Yeah, these are becoming more important for integrating renewable energy sources like solar panels directly into local grids.
But stability is an issue.
It can be. The interaction between power converters, loads, and the network itself can lead to instabilities. Ensuring the grid remains stable under varying conditions is crucial.
How does AI help?
They used a digital network twin, a detailed simulation of the microgrid to generate data on stable and unstable operating conditions.
Then trained an AI on that simulated data.
Exactly. They used random forests, a type of machine learning model, as a surrogate model to learn the relationship between grid parameters like controller settings and stability.
So the AI figures out what causes instability.
It helps identify the key parameters influencing stability, providing insights for domain experts. Then they used Bayesian optimization again, this time guided by the random forest model, to find parameter settings that maximize the stable operating region of the grid.
And validated it in the real world.
Yes, they showed results from a laboratory testbed that confirmed the effectiveness of the AI-based optimization approach.
Cool. Chapter 15, Self-Optimization in Adaptive Logistics Networks, Making Supply Chains Smarter.
Pretty much. This one focuses specifically on spare parts inventory management.
Spare parts demand seems tricky to predict.
It really is. Parts might have fluctuating life cycles, demand can be intermittent, traditional forecasting methods often struggle.
What's the AI approach here?
They used hierarchical Bayesian models. These models can capture complex demand patterns and, importantly, allow for information sharing between similar types of spare parts. If you have data on one part, it can help inform predictions for a related part.
Does it group similar parts automatically?
They used clustering methods on historical data to identify typical demand patterns first. Then the Bayesian model forecasts future demand based on these patterns.
And then optimization.
Right. Step 2 is formulating an optimization problem to find the most cost-effective ordering policies, considering the demand forecasts and things like production costs. They looked at extending standard inventory models to handle uncertainty and nonlinear costs.
Chapter 16 brings us to underground train systems. Optimization again, but for trains.
Yes, specifically optimizing energy consumption and timetabling, working with the Nuremberg public transport operator, actually.
How can you save energy with trains?
A big way is by optimizing the velocity profiles, how quickly they accelerate and brake between stations. Also, coordinating trains to maximize the use of regenerative braking, where a braking train sends power back to the grid for another accelerating train to use.
How do they optimize this?
Using mathematical programming, specifically mixed integer programming, MIP, the models figure out the best departure times and speed profiles while making sure timetables are met, connections work, and safety distances are maintained.
Did it show significant savings?
The case studies demonstrated benefits from optimizing both voltage control at substations and the individual train speed profiles. But there's always a trade-off. Saving energy might mean slightly longer travel times.
Makes sense. Chapter 17, AI-assisted condition monitoring and failure analysis for industrial wireless systems, keeping factory Wi-Fi reliable.
Basically, yes. Industrial Internet of Things, IoT, relies heavily on wireless communication, but factory floors can be harsh radio environments with lots of interference. Ensuring reliable communication is critical.
So AI helps diagnose problems.
That's the goal. Building systems that can monitor link quality and automatically analyze failures. A challenge is getting the right data sets for training these systems.
What kind of AI techniques?
They propose analyzing data from multiple layers, from the raw radio spectrum up to network protocols. One approach used unsupervised learning with autoencoders to detect missing data frames by learning what normal communication looks like.
And analyzing the radio signals directly.
Yes, using machine learning, specifically image recognition techniques applied to spectrograms, visual representations of radio signals over time, to detect things like Wi-Fi frames and, importantly, collisions or interference.
Chapter 18 sounds massive. XXLCT scans for machine learning and non-destructive testing. Huge 3D X-rays.
Exactly. Computed tomography, but on a very large scale. Think scanning entire vehicles or aircraft components to look for internal defects or analyze structures without taking them apart.
What are the challenges with such huge data?
The sheer size, obviously. These are large, complex 3D volumes, and often there's a lack of labeled data knowing exactly what's what inside the scan. Annotation is a major bottleneck.
They scanned a plane and a car.
Yes, a historical Mi-163 aircraft and a Honda Accord were used as examples. They explored different annotation pipelines, manual, semi-automated, and fully automated to label materials or objects within the scans.
What AI models did they use for analysis?
3D units, a type of convolutional neural network adapted for volumetric data, were used for semantic segmentation, basically classifying each voxel 3D pixel in the scan.
And the results.
They showed promising results for the UNet architecture in identifying different entities within these complex CT volumes, even on unseen data.
Finally, Chapter 19, Energy-Efficient AI on the Edge, making AI run on tiny devices.
Exactly. Edge computing running AI directly on sensors or small devices with limited power and processing capabilities, it's a huge trend.
Why is energy efficiency so critical here?
These devices often run on batteries or have very strict power budgets. You need to optimize not just the AI's accuracy, but also its resource footprint, energy use, memory size.
How do you design energy-efficient AI?
One approach presented is an AutoML tool, again using evolutionary algorithms, but this time specifically optimizing for energy efficiency in classical machine learning models. It uses a clever energy prediction model based on analyzing the assembly code instructions.
Predicting energy use from the code.
Yeah, using a technique called implicit path enumeration on the code's control flow graph. They showed an example of classifying device usage on a tiny resource-constrained tag with minimal power draw.
What about deep learning models on the edge? They're usually big.
Right, so deep compression techniques are key. Things like pruning, removing unimportant connections or neurons, and quantization reducing the precision of the numbers used in the model. For example, using 8-bit integers instead of 32-bit floats.
Different types of pruning.
Yes, element pruning, removing individual weights, versus structured pruning, removing entire filters or channels, which can be more hardware friendly. And for quantization, there's post-training quantization, done after training, and quantization-aware training, where the model learns to be accurate even with lower precision.
And software to run these optimized models.
They mentioned Done Runtime, a custom runtime environment for embedded devices, and benchmarked it using things like MLPerf Tiny. The overall goal is bridging the gap between data scientists designing models and hardware engineers deploying them efficiently.
Wow. That's an incredible breadth of research covered in this collection. It really paints a picture of AI moving well beyond theory.
Absolutely. From designing itself with AutoML to learning from experience, dealing with messy real-world data, ensuring safety, and even running on tiny devices.
Let's quickly recap some of the most, maybe surprising or fascinating insights for someone new to the depth of this.
Okay, first, the whole idea of AutoML AI designing AI systems, that's pretty meta.
Definitely. Second, how deep learning is getting really good at finding complex patterns in time series data across so many different fields.
Third, reinforcement learning agents learning effective strategies just through trial and error without explicit instructions. It's powerful.
Fourth, the progress in learning effectively even when you have very little labeled data using SSL and active learning, that opens up a lot of possibilities.
Fifth, the ability to actually quantify the uncertainty in AI predictions. That's huge for building trust and for safety.
Sixth, using AI to automatically discover and analyze complex business or operational processes from raw event data process mining.
Seventh, the crucial role of mathematical optimization techniques working alongside AI to solve really tough real-world scheduling, routing, and resource allocation problems.
Eighth, the increasing use and sophistication of synthetic data generation to train AI when real-world data is scarce or expensive.
Ninth, the focus on making AI robust and reliable enough for safety-critical applications like autonomous driving and pathology, including ODE detection and uncertainty estimation.
And 10th, the push towards energy-efficient AI that can run effectively on resource-constrained edge devices. AI everywhere, basically.
That covers a lot of ground. It really shows how diverse and impactful AI research is becoming across the board.
It certainly does. The potential benefits span nearly every industry we've touched on. So here's a final thought to leave you with. As AI continues to evolve at this pace, embedding itself into more and more aspects of our lives, from driving our cars to managing our power grids, how will our own understanding of intelligence, automation, and maybe even trust need to adapt alongside it?
A big question. Definitely something to mull over. Hopefully this deep dive has sparked some curiosity for you to explore some of these areas further.